This is AP Calculus AB, and in this video I'm going to talk about section 7.4, exponential growth and decay. And the main focus in this section is going to be application problems of our separable differential equations. But you are going to see some problems like these first couple of examples that we're going to go through. These are very much like the group quiz that you guys did last time, where you were essentially working on separable differential equations and doing a little bit of algebra sometimes to solve for the y. So you've got some of these in this section where it's a little bit more work to actually go through and get your y isolated, and then you'll also see some of these that will involve things like use substitution when you're solving them out. So I wanted to go through a couple of these with you just really quickly and make sure everybody's clear. We talked about the steps, but I just want to reiterate how important showing all these steps are. So we have this separable differential equation, dy dx is 6y squared x. Solve for y if x is 1 when y is 1/25. So what we're going to do here first is separate our variables. And when we do that, we're going to end up with dy over y squared. And that's going to be equal to 6x dx. Now the 6 could have gone on either side. It wouldn't really matter. The algebra that I used to get to the end resulting y would be a little bit different, but in the end, I will get an equivalent answer. Okay, so I'm taking the indefinite integral on both sides. On the left side, I'm going to get negative 1 over y. And on the right side, I'm going to get 3x squared plus c. Now, I've mentioned before, you can take your equation and solve for c anywhere you really want to. Here, since I have a y of 1/25, it probably makes sense to go ahead and plug it in now because it's going to simplify down really nicely if I plug that 1/25 in right now. And what will happen is on the left side, I'll get negative 25, and that would be equal to 3 plus c. And from that, I can see that the value of c would be negative 28. Okay, so what I've got here is negative 1 over y is equal to 3x squared minus 28. And then I just need to solve for y. Now this one's a little bit different, right? Because we've got the y in the denominator. So what I'm going to do is I'm going to take the reciprocal on both sides. And on the left side, I'm going to get y. I'll explain what I did with the negative here in a second. And on the right side, I'd have 1 over all of this, 3x squared minus 28. So I'm essentially taking the reciprocal of both sides of the equation. And then I'm also going to multiply each side by negative 1. And that would be my particular solution to that differential equation. Okay, so remember, you've got two ways to check that. You can plug in x is 1 and make sure you get y is 1/25. Also, if I take the derivative, it should simplify down into 6y squared x. So that would be a little bit of work on this one because we've got a more complex differential equation. But if you really wanted to, you could check the answer. Just note, as always, I showed the separation of variables. I showed where I solve for my c. I showed where I solve for my y. So all of those key things that I have been mentioning, those are still there. Okay, so let's take a look at another one. We have dy dx is y squared plus 1. Solve for y if x is 1 when y is 0. Okay, so also fairly simple here because it's easy to separate the variables. But notice y squared plus 1, if I want to move the y squared to the left-hand side of this equation, and get it grouped with the dy, I can't just subtract y squared. What I actually have to do is divide by y squared plus 1. And what that leaves on the right side is 1 times dx, or just dx. And then from there, I can integrate. And when I integrate on the left side, that's essentially 1 over y squared plus 1. So I'm going to have an inverse tangent of y is equal to x plus c. And like I mentioned on the last one, we can plug in our point whenever we want. I'm going to go ahead and plug this in because I know what inverse tangent of 0 is. Inverse tangent of 0 is equal to 1 plus c. So inverse tangent of 0 is 0. So from that, I can get c to be negative 1. And then I can solve for my y here. So let me show you with the negative 1 plugged in first. We would have inverse tangent of y is equal to x minus 1. And now I'm going to isolate the y. So I'm going to take the tangent on each side, and I'm going to end up with y is equal to the tangent of x minus 1. So all I did was essentially did the inverse operation of an inverse tangent, which would be a tangent. And that tangent and inverse tangent canceled out on the left side. It left me tangent of x minus 1 on the right side. Okay, so you'll see some of these separable differential equations in this section. Like I said, the algebra is a little bit trickier, but it's still the same general idea. Now, the main focus in this section is going to be application problems. And what we're going to look at for today, we're going to look at one differential equation that is going to be used for just general exponential growth and decay. And this is the the differential equation we're going to use. dy dt is equal to k times y. And what this is just basically, it can be exponential growth or exponential decay, depending on whether that proportionality constant k is positive or negative. But the steps are already done here. I'm going to solve this one out, right? So I would separate the variables, and I get 1 over y dy is equal to k dt. Integrate on both sides. On the left side, we're going to get a natural log of absolute value of y is equal to kt plus c. And now we talked about this when you guys went through your group assignment last time. When you are now isolating the y, the first thing I did was I exponentiated on both sides of the equation. The exponential with a base e and the log are going to cancel out. So I'm left with absolute value of y is e to the kt plus c power. And then the e to the kt plus c can be rewritten as e to the c times e to the kt power. And then what I'm going to do here all in one step is I'm going to drop the absolute value, which makes the right side plus or minus. And then so the plus or minus e to the c all just becomes this new arbitrary constant a. And then the last thing is I would need to solve for that a. Well, if I knew that the initial y value was y naught when time is equal to 0, if I solve for that a value, I'm going to get y naught. So y is equal to the initial y value times e to the kt power. Okay, if we have a k value that is positive, we have exponential growth. If we have a k value that is negative, we have exponential decay. Now, that differential equation is going to be used on almost every single one of these problems you're going to see for today. And when you work out these problems, they essentially turn into algebra problems because you don't need to do all of these calculus steps. They're exactly the same every time. And I'll show you what I mean by that. Okay, so here we've got a problem that says the number of bacteria in a culture is increasing according to the law of exponential growth. There are 150 bacteria in the culture after 3 hours and 400 bacteria after 5 hours. So it says write an exponential growth model for the bacteria population. Well, I'm using population, but it's still the same general idea. Population would be equal to the initial population times e to the kt power. Okay, so I still have exactly the same as what we had up above. Now, you guys did a lot of problems like this in Algebra 2. Now that we've sort of skipped all of the calculus steps, this just turns into an Algebra 2 problem. So I'm going to plug in what I know here. I know I have a population of 150 in the culture after 3 hours. So that would be equal to my initial population times e to the k times 3 power. And I also know that I have 400 bacteria after 5 hours. So that'd be p naught e to the k times 5 power. So what I've got here really is a system of equations. And now I just have to do some algebra and solve this out. You can actually divide these two equations if you want. And what you're going to end up with is 150 over 400 would be equal to e to the negative 2k power. And from that, I can solve for k. K would be approximately 0.4904. And now I've got my growth model. My population at any point in time would be equal to, and I'll explain the p naught here in just a second, e to the 0.4904 t power. And then for my initial population, since I got the k value and I've got this system of equations right here, I can just go back and plug into either one of those and solve for the initial population. And it would be about 34.446. Okay, so very, very simple to do. Like I said, it's essentially an algebra problem because once we understood that it was the law of exponential growth, we can go straight to that population model, and we don't have to do any of the calculus to get there. Okay, so part B, it said find the initial population and the growth rate. You can see I already did that in part A. And then on part C, after how many hours will the bacteria count be approximately 15,000? Well, I know what my model is, so I'm going to set my population equal to 15,000. That would be equal to 34.446 times e to the 0.4904 t power. And then I can solve for t, and we would end up with time being approximately 12.4 hours. Okay, so again, it's just an algebra problem. So I showed you some of the algebra steps on that one. For the rest of these, I'm not really going to go through the algebra steps because you guys know how to do that stuff. But that's really what the majority of these problems are going to be like when we look at applications of differential equations. All right, so we also have this whole idea of compounding interest. And you may or may not remember this from Algebra 2, but we can have interest compound at different intervals. And what we're looking at with this first equation, we're not really going to use this one much, but it's just kind of a bridge to get where we want to go. The amount of money we have at any point in time is equal to the initial amount times 1 plus r over k to the kt power. So that's an exponential growth model. And it says we have $1,000 invested at 6% compounded monthly for 3 years. So what we want to do here is we want to figure out how much money would we have at the end of 3 years. Well, the amount after 3 years would be equal to the initial amount, 1,000, times 1 plus our interest rate, which is 0.06 over k. Now, the k, in this case, when we're talking about compound interest, this value that you see here is going to be the number of times our interest compounds per year. So in this case, that would be 12. And that's going to be to the 12 times 3 power because, again, k was 12. And that gives us an amount after 3 years of approximately $1,196.68. Okay, now notice that didn't follow our same exponential growth model that we had been accustomed to. That's when we compound our interest. You know, we can do it daily, we can do it monthly, we can do it weekly. But the idea there is we're compounding it at different intervals. Well, the one that we're really going to use is when we compound continuously. And notice what happens to our differential equation when we compound continuously. We end up with this rate where the rate of change of the amount of money we have is equal to that rate times the amount that we have at that particular point in time. Well, if that's the case, notice that looks just like our dy dt is equal to k times y. So I have an initial amount of A naught. I already know what my model is going to look like for my money. The amount I have at any point in time is going to be equal to A naught e to the kt power. Okay, so exact same thing as we had before. I guess we should use RT there since we have an R. But other than that, it looks exactly the same as what we did before, right? So not really any difference. So if you have a problem like this one, it says find the amount of time required for $10,000 to double if the annual interest rate is compounded continuously. All you have to do is plug into that equation. We don't even have to figure out the equation. We already know what it is. So you'd have 20,000 equal to, we started with 10,000 e to the, let's see, they didn't give us a rate here. So I'm going to assume that the rate is the same as the previous part of this problem. So we're going to say it's a 6% interest rate times t. And then from there, we can solve for t. So t would be about 11.55 years. So it takes approximately 11 and a half years to double your money at a 6% interest rate if your interest is compounding continuously. Okay, so the idea there, you know, connecting these two things that we did, the first part of this, we're not really going to do the compounded interest. But what it allows you to get to is the idea that if I start making those intervals where I'm compounding my money smaller and smaller and smaller, like we can talk about, you know, compounding yearly, monthly, weekly, daily, hourly. We could compound by the minute, by the second. And so essentially what we're doing here is we're saying, okay, now we're going to compound continuously. We're going to make that time interval infinitely small. And this is what the model turns into. All right, so the last type of application we're going to look at today is radioactive decay. And notice that we have the exact same model again. Now, radioactive decay is when we have some sort of a radioactive material that is decaying away over time. So it follows the model. dy dt is k times y. In this case, k is going to be a negative value because we have exponential decay. So if I solve that differential equation, we already know what the solution is going to look like. We know the k will be negative. Okay, so if I want to find the half-life, which is something that's really common on these questions, that means I'm going to have half of my initial amount left, right? So what we did here was we took the amount that we have at any point in time and we set it equal to half of the initial amount. And now we just want to figure out how long does it take for that to happen. Well, if we solve this for t, so you can see that the initial amount divides out of both sides. We can take the log on each side and we get kt as natural log of 1/2. And now we have time in terms of our growth constant k. So time is natural log of 1/2 over k, or time is negative natural log of 2 over k. Okay, so that's our relationship. Now don't feel like you have to memorize these. Those are not things we're going to use that often. What you should know is that if they're talking about half-life, then I need to set my amount that I have at any point in time equal to the half of the initial amount. And then you can go through and do the algebra for the rest of that. Some people try to memorize t in terms of k. It's really not necessary and it's not useful for you because the odds of you seeing this again after this unit are fairly low. And even if you did, it's so easy to get t in terms of k, it's really not worth the effort to try to memorize it. All right, so let's just take a look at an example of this. You've got one or two of these in your assignment. The half-life of cesium-137 is 30 years. Suppose we have a 100 milligram sample. Find the mass that remains after t years. Okay, so what we would have to do here is we would have to solve for the k value, right? So that's what I would do here is solve for k. And when we solve for k, I'm just going to tell you what this turns out to be here. K turns out to be approximately negative 0.0231. Okay, that would be your k value. Now, the way I solved for that is I just used this setup right here. I set my amount equal to half of the initial amount, and I can get that k value. And now I have my model for the amount that I have at any particular moment in time. It's 100 e to the negative 0.0231 t power. Okay, so then B, how much of the sample remains after 100 years? Easy, plug in time is equal to 100, and you get the amount at time is 100 to be approximately 9.926 milligrams. Or on part C, how long will only 1 milligram remain? Well, on that, I would just say, okay, I want 1 to remain. Set that equal to 100 e to the negative 0.0231 t power. And again, it's just an algebra problem. We get here, time is approximately 199.358 years. Okay, so as you go through your assignment, anytime you have these types of applications where they're following this exponential growth or exponential decay model, then you don't have to work through all the steps. Now, you are going to see a couple of applications where they're going to give you some problems where your growth models are not going to be exactly the same. And in that case, you would just have to solve the differential equation, and then at that point, it turns into an algebra problem. So you will see both types, but primarily it's just going to be using that one differential equation, dy dt is equal to k times y.